Welcome back to the Tutor Wizard. What we're going to do is, this time we're going to do a final exam review problems. We're going to do a whole bunch of problems. This will be a good benchmark for the types of problems on a typical Calculus 1 final exam. The first one we're going to do is Riemann Sums. What does that mean? Basically, that means we have to use Riemann Sums. To do that, we're going to set up, first of all, I have f of x is x squared plus 3x. To do Riemann sums, remember I need f of xi star and I need delta x. So first of all, the thing that we're going to do is I see that b is 3 and a is 1, the limits of my integration. Delta x is always equal to b minus a over n, which is, in our case, 3 minus 1 over n, which is 2 over n. So let me write that down. Delta x is b minus a over n, which is 2 over n in this case. 3 minus 1 is 2. This gives me delta x. Now I need f of xi star. First of all, let's do xi star. Xi star is some sample point in our interval. Remember, we're integrating our function from a to b, and then we're chopping it up into these rectangles. Each rectangle has an area. The width of the rectangle is delta x. The height of the rectangle is f of xi star for some sample point. I'm going to pick the right-hand endpoints as our sample points. Using that, how do I get there? I have to travel a distance of a, and then delta x I times. So using right-hand endpoints, xi star, our sample point is a plus delta xi. In our case, a is 1, so that gives us 1 plus delta x was 2i over n. Delta x was 2 over n times I. So this is our xi star. Notice in this one they're being mean. They didn't give you 0. If I have 0 here, it's nice. I don't have a 0 here. I won't have to FOIL anything out. As soon as they give you a non-zero a, I'm going to have to FOIL everything in our function. Now xi star goes into f of x. F of xi star is equal to f of 1 plus 2i over n. That is now f is this quadratic. This is 1 plus 2i over n squared plus 3 times 1 plus 2i over n. That ends up becoming, I'm going to FOIL this out or multiply it by itself. Take your time. 1 plus 2i over n, 1 plus 2i over n, plus 3 plus 6i over n. I've distributed this 3 in. Do it baby steps at a time. What does that give me? I move it to the top. This is equal to 1 plus 2i over n plus 2i over n plus 4i squared over n squared plus 3 plus 6i over n. I'm going to combine everything. These can all get combined. I have 4i over n and 6i over n, so this is going to become, I'm going to group these together, 4i squared over n squared plus 10i over n plus 3 plus 1 is 4. This is what I got. This is f of xi star. Delta x was 2 over n. Now what I have to do is I need f of xi star times delta x. Let's clean that up. So f of xi, this tells me that f of xi star times delta x is equal to 4i squared over n squared plus 10i over n plus 4 times 2 over n, which gives me let's distribute this onto everybody, 8i squared over n cubed plus 20i over n squared plus 8 over n. This is f of xi star times delta x. Why do we do that? Because now that I've chopped all of these things up, now I'm going to put it into the pot. Basically, I had to chop up the onions and the potatoes and the carrots and everything, and then I put them together, and I put them into nice piles. Now we're going to put them into the soup and stir the pot. Cook some lunch. What do I do with that? Now I put it into the machinery of the definition of definite integral. That is specifically the integral from 1 to 3 of x squared plus 3x dx is equal to, by the definition of definite integral using Riemann sums. The limit as n approaches infinity of the sum from I equals 1 to n of f of xi star times delta x, which is the limit as n approaches infinity of the sum from I equals 1 to n of this hot mess, is what we put in there. 8i squared plus n cubed plus 20i over n squared plus 8 over n. Now I don't need this. Get out of there. From here, the idea is I distribute the sum onto all of these sums. So let's do that next. Equals the limit as n approaches infinity of the sum from I equals 1 to n of 8i squared over n cubed plus the sum from I equals 1 to n of 20i squared over, or I over n squared plus the sum from n equals 1, I equals 1 to n of 8 over n. So I've distributed the sum onto all three terms. Sigma. Now, at first this is strange, but this sum I is changing, so we can't move this out, but the 8 and the n's you can move outside of the sum, so we can get this closed forms for the sums. And then usually they'll give you the formula. If they're nice, they give you these sums of i's on the formula sheet for the final exam. If not, memorize these. This is equal to the limit as n approaches infinity of 8 over n cubed, the sum from I equals 1 to n of I squared, plus 20 over n squared, the sum from I equals 1 to n of I, this guy by itself, and then plus 1 over n or 8 over n, the sum from I equals 1 to n of 1. Now I use the forms of the closed forms for these sums. Carl Friedrich Gauss gives this one at age 5 roughly. He says the sum of this, the first n integers is n plus 1 over 2. He cleverly gives this. We'll show you this story in a different video. This is equal to, now, the limit as n approaches infinity of 8 over n cubed. The sum of I is n plus 1, 2n plus 1 over 6, plus 20 over n squared, n plus 1 over 2, plus 8 over n times the sum of this 1 is n, if we add 1 to itself n times. Close bracket. What does that give me? Again, now that we've got rid of all the closed forms for i's, we have now n's. Now I can simplify this expression and push n to infinity and see what number we got, the area under the curve of this function from 1 to 3. Let's do that now. This thing becomes, I'm going to write it like this, equals the limit as n approaches infinity of 8 over 6. First of all, I'll get the numbers to the front. Now I have n plus 1, 2n plus 1 over n cubed, which is n, and n is how I'm going to write it. You'll see why in a second. Plus 20 over 2, which will simplify n plus 1 over n times n, plus 8n over n. If we do it that way, one of the n's will cancel, and we get equals the limit as n approaches infinity of, let me rewrite that, equals, divide by 2, 4 over 3, the limit as n approaches infinity of n plus 1 over n, 2n plus 1 over n, plus 10 times the limit as n approaches infinity of n plus 1 over n, plus the limit as n approaches infinity of 8. What I did now is distribute the limit onto all of these sums. This pen is dying. Let's give me another one. What does that do for me? We're taking n to infinity, and these are all proper or improper rational functions. The degree on the top is the same as the degree on the bottom. I'm going to write it like this, equals 4/3, the limit as n approaches infinity of 1 plus 1 over n, 2 plus 1 over n, plus 10 times the limit as n approaches infinity of 1 plus 1 over n, plus, I know, it's exciting, we're almost done, that's Willa again, plus 8 you don't know how to do Riemann sums, be quiet. There should be a bracket there. What does that give me? These all go to 0 at infinity. So this is equal to 4 over 3 times 1 plus 0 times 2 plus 0 plus 10 times 1 plus 0 plus 8, which is equal to, what do I get? 8 over 3 plus 18. How do I add this? I need a common denominator. Favorite dirty trick, 3 times 3. What's 18? Don't use a calculator. Do it in your head, or do it like this if you have to. I get 24, and I get 54. So this should be, and what's plus 8? Oh, let's carry. Then I get a 2, carry the 1, I get 6. So this is 62 over 3. Next question. Question 2 is going to be compute the derivative of this function. Let's retry that. Compute the derivative of g of x, which equals this guy. How are we going to do that? We're going to use the fundamental theorem of calculus part 1, which says you can take derivatives. First of all, let's do a small tangent there. What is that really saying? The fundamental theorem of calculus says if you have this weird function g of x, let's start at the very beginning. An antiderivative, f has an antiderivative of if what? So if I have a function f of x, big F of x is the antiderivative. I know, it's exciting. Big F is the antiderivative of f if what? If f prime of x equals f of x. It's the antiderivative. The fundamental theorem of calculus part 1 says if you have this function g of x, which equals the integral from a to x of f of t dt, the area computing function under f, here's a to b, and then if I do this to x, it's computing this. This is what this guy does. He computes the area under f of t. What the fundamental theorem of calculus part 1 says is that the derivative with respect to x of g of x is the derivative with respect to x of the integral from a to x of f of t dt, which it says is f of x. The derivative of g is f. What does that say? That's fundamental. They call it the fundamental theorem of calculus. What it's saying is that this general antiderivative of a function f is the area computing function of that function f of t. G is the derivative of f, so g is the antiderivative, and g is the area computing function. What it also tells me is they got a clever rule where they can make you do the chain rule or something like this. Also, I noticed that this function, if you haven't seen exponential functions, you won't know how to take the derivative of this guy, but we can change it to another guy that you would know how to take the derivative of, and we'll see how the rule works either way. But if you don't know how to take the derivative of 2 to the x because they didn't do it in your class, just put cos there or some function you do know how to integrate. It's the chain rule is basically what we're doing. You're going to see. So this is what I'm going to use, the fundamental theorem of calculus part 1. G prime of x in our case is the derivative with respect to x of the integral from 1 to 2 to the x t cos t dt. Now what you have to see also is if I called, so we're taking the derivative of that thing, and it's the chain rule. So let me do the move and then I'll explain why that has happened. If you haven't seen why this is happening. This says that I'm allowed to write this as the derivative of this thing is equal to, I just put whatever's here into where t is, so I just get 2 to the x cos of 2 to the x, but now times the derivative of 2 to the x, which is equal to 2 to the x cos 2 to the x times 2 to the x ln 2. The derivative of every exponential function is proportional to itself, and the proportionality constant is log a, or log 2 in this case, because the base is 2. Why did I do this weird business at the end where I used, it seems like I used the chain rule is in fact what I used. So call the function temporarily h of x equals the integral from 1 to x of t cos t dt. And then call k of x equal to 2 to the x. So this is the answer, first of all, to that problem. I'm going to erase it. then what I want to do is, what if I did h following k of x? How do I do that? Composition. All of a sudden it becomes extremely useful in this scenario. This is h of k of x, which is what? H of what does k do? 2 to the x. And then where do I put that? Wherever there's an x in the expression for h, so that becomes the integral from 1 to 2 to the x of t cos t dt. The point being is, do you see, this horrible expression is the composition of two functions. So if I want to take the derivative of this, I'm taking the derivative of composition, so it should be the chain rule. And that's exactly what's happening. When I want to take the derivative of that now, the derivative with respect to x of this thing, the integral of, and that's why I put the brackets so that you can see t cos t dt, is the derivative of the inside evaluated at the, or the derivative of the outside evaluated at the inside times the derivative of the inside. This is the outside function. This is the inside function. So this is going to be, I do the derivative of this by the fundamental theorem of calculus part 1. This is just 2 to the x. I put whatever's in here where t was. Cos 2 to the x times the derivative of the inside, which is 2x ln 2. This is how we use the fundamental theorem of calculus part 1. Taking derivatives, using composition usually. Next question. Number 3 wants us to compute derivatives using substitution rule, or they probably aren't going to tell you that on the exam, but I'm pretty sure that the only technique you have is the power rule for integration, the integral of sine and cosine, and then you're going to use substitution rule. So what we want to do for substitution rule, both of these I'm going to use substitution rule, and then this one's a little bit weird where I have to fudge the definitions of what the substitution is and is resolve, and it gets a little more complicated. What they're saying is, if you have an integral and you have some outside function, and then your function, you can see a function inside that more complicated function. In this case, the outside function is going to be g of x is going to be square root, and then I see my function inside. And then if you can see somehow the derivative of your function on the outside, then I can write u equals f of x, and then the differentials are du equals f prime of x dx, which is exactly what I have. And we're going to liquidate x, all x's must go. And they say that we have a theorem that this says this is g of u du. We can substitute. First of all, the point of doing it is we can't integrate this thing, but I can see cleverly a function and its derivative in the expression. So ironically, to do the first technique of integration, I have to be good at differentiation. I have to see the pairs of the function and its derivative and know what those pairs are so that I can see it in the problem to integrate and do the move. Why have we done the move? The move says usually when you do that, it will give you a way to either, in more complicated ones if you take the next class, to do more techniques to get the antiderivative, or in these ones, in one move, it will give you a function which now is back on your lexicon of integrals you should know how to do, which at this stage is the integral of sine, the integral of cos, and the integral of x to the n, where n is -1. Let's use this machinery on these two guys. 1. The integral of cos x over sine squared x dx. What I see is if I let u equal sine x, then I have the derivative cos x dx. That's exactly what I want to see. Who's the g function? 1 over x squared. This tells me that using this substitution, this equals the integral of 1 over u squared. U is sine. Times what is cos x dx? du. And this is now a negative exponent law. Why we did the move is now that I didn't know how to integrate this, I do the clever substitution, and now it's just a power rule. This exponent is not -1, so I can use the rule. What is the rule? Let's do that explicitly. The rule is we write this as equals 1 over -2 plus 1 u to the -2 plus 1 plus c, a constant of integration. Then I clean this up. This gives me -1, which I can write on the top, and this will be 1 over u plus c. What was u? U was sine x, so this gives me -1 over sine x plus c, or I guess I could write that as negative cosecant x plus c is the final answer. You don't have to write doing it. First of all, you don't have to do the last step with the fancy steps, but what they do usually want is if you started in variable x after you do the substitution, they want you to put it back into the substitution so that you have the variable x as your final answer. The second one, the integral of x cubed square root 1 plus x squared dx. First of all, nobody likes to do this, and that's why they've done it, but they're not going to catch me. Nobody likes to separate the x cubed. First of all, I write this as x squared, the square root of 1 plus x squared times x dx. You're like, how did you move one? I split x cubed as x times x squared, which I'm allowed to do, and then I move this one over. You can commute everything. Why have I done that? Because now I can see that this function, if this was my u, I have the derivative up to the constant 2, which I can fudge around. I'm going to let u equal 1 plus x squared, then du equals 2x dx is what I'm talking about. I only have x dx. Well, luckily 2 is not 0, so divide both sides by 2, and we get 1/2 du is x dx. You're like, well, how am I going to get rid of this guy? Well, u is 1 plus x squared, so x squared is u minus 1. And now we're in business. We can liquidate x, all x's must go. This equals the integral x squared was u minus 1 times the square root of this guy was u to the square root, or u to the 1/2 times 1/2 du. I don't need the substitution, I'm going to erase it. There it is. This is equal to 1/2. I take the constant out of the integral. And then this is the power rule. This is u to the 1 plus 1/2 is 3/2 minus u to the 1/2 du. Now it's the power rule again. All I have to do is, what does that become? You should start doing these, but it'll be 1 over 3 over 2 plus 1, which is 2/5. U to the 5 over 2 minus 2/3. U to the 3 over 2 plus a constant of integration. What was u? U was this guy, equals 2 over 5, 1 plus x squared to the 5 over 2 minus 2 over 3, 1 plus x squared to the 3 over 2 plus c squished in there. I keep saying it, we're going to get a bigger board. This is how, notice again, once I make this substitution, I sub back to the final answer being in x, because they started in x. This is the substitution rule. Next question. Number 4 is going to be, I finally remember what number it was. I had to go upstairs and get the editor to actually tell me what number I'm on. Counting to 4 apparently is hard. Calculus is not. I don't know how that works. This number 4 is we're going to use Rolle's theorem. We don't need intermediate value theorem, but this is the scenario where I might need intermediate value theorem and I might need Rolle's theorem, and depending on what they say. In this, also these questions, there's a problem and there's a logical problem in here. At least, at most, and exactly 1. In this case, they want at most. I have at most 10 BMWs in my backyard. That means I don't have 11 or more BMWs. It's valid to have 0 BMWs, which is the true case. I don't have any BMWs. But I have at most 10, because at most 10 means I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10, but I definitely don't have 11 BMWs. That's at most. I don't have to show that I have any. I could have any number of BMWs from 0 to 10. All at most 10 means is I don't have 11 or more BMWs. Here it says, shall we have at most 1 real root in the interval -2, 2. So all that means is I have to show I don't have 2 or more. I don't know if I have 1 or 0 roots in that interval, but I know I don't have 2 or more roots in that interval. How do we do that? Because I don't have to show the existence of any of the roots, I don't need to use intermediate value theorem to show the existence of these. So I'm not going to try to show there is 1. At most says I just have to show that there are not 2 or more. So that's exactly what I'm going to do. Assume, well, I'm going to use Reductio Ad Absurdum. We get to use some Latin to proof by contradiction. Reductio Ad Absurdum is quite literally reducing the argument to an absurdity, and therefore that can't be true. Zeno, the Greek, actually used to do it in politics. This comes out in political sciences, actually. What Zeno does is he says, Politics 101. Never try to, when you're in a debate, convince the other side of your argument. This is ridiculous. They're ready to come toe-to-toe with you. What you do is you'll never convince them of your argument, so I tear their argument down. And what Zeno does in politics and what I'm going to do in this scenario is tear this argument down. So what Zeno would say is, let me hear your political argument or your view on what's going on. What he would do is take that assumption, reduce it to an absurdity, and therefore your assumption can't be true. So he's never arguing his point, he's just showing that your point is garbage and it has to be torn down because it has an absurdity in it. We're going to do exactly that here with just roots, not people in politics, and trying to prove things about how to deal with coronavirus outbreak. What we're going to assume is the opposite of what I want. It says we have at most one real root. So let's assume we have two or more and reduce it to an absurdity. Assume we have two or more real distinct roots. So real means that they're in the set of all reals, and distinct means, we'll write it for emphasis, x1 doesn't equal x2, and then immediately, like, who's larger without loss of generality, I'm going to let x1 be the smaller one because the index was smaller. Without loss of generosity. That's a joke for another time. Somebody used to, I was lost in translation. Someone I know used to always say, without loss of generosity. It's like, yeah, we're going to keep it generous, but we're still doing it. What can I get from this assumption? Now we're going to use Rolle's theorem. It's the bump theorem. I now have an x1 and an x2. The picture really helps me also. And what it says is we're going to have these conditions. Rolle's theorem says if your function has two values where they're equal at 2 points, f of a equals f of b, and then your function is continuous in that interval, so you can't lift your pen to do it, and then you had to come back on yourself somehow, and then you are actually differentiable in that interval so that I can talk about your derivative. It says there has to be some c in there where there's a horizontal tangent line, there's a bump on your function, and that's going to say, oh, we ran into it. That's going to say the derivative is 0. And so now this is confusing because we're talking about our function being 0 here at this point. And then we're talking about our function being 0 here. And then we're talking about our derivative being 0 here. Let's recap that one more time. I'm assuming that I have two or more real roots. And now this is the picture. Because one, Rolle's theorem says you have to have f of x1 has to equal f of x2, and they do because cleverly they're both roots. They're both 0 for my function because I've assumed I have two of them. Second, it says you have to be, f has to be CTS continuous in the interval, closed interval x1, x2. And then 3, f has to be differentiable in the open interval x1, x2. Is that true for us? Yes, our function is a polynomial. It's continuous on R, so it's continuous in any subinterval of R. It's differentiable on R, and therefore is differentiable in this interval. So our function satisfies Rolle's theorem in this assumption. And now we're going to get a contradiction, and I need two statements for that contradiction. Statement 1 is Rolle's theorem. Rolle's theorem says if you assume you have two real roots, which are distinct, our derivative is 0 somewhere, is what that says. I can erase the picture, and then this by Rolle's, and we write that so that you don't just try to, I was guessing and I was hoping you'd give me marks and a check mark. No, that tells me you knew what you were trying to use intellectually. I'm using Rolle's theorem and the conditions. That tells me there is C inside x1, x2, I'm squeezing it in there, in that interval, such that the derivative is 0. How am I going to get a contradiction for that? I need to have another statement which says that can't be true. And then I'm going to be like, how could you have this and this at the same time? And this is where everybody forgets. You get so worked up that you can finally find your way through Rolle's theorem. And what do I do to contradict this now? This one's extremely mean, and I'm glad we got to do this one this time because there's the outlier. Our derivative is 0 sometimes. Usually the argument is, oh look, it said the derivative is 0, and then I compute the derivative and then it's not 0. Well, it's going to be 0 sometimes here, but not in here. It's going to be the key. So the first thing I did was I used Rolle's theorem to show that my derivative has to be 0 somewhere in the interval. Remember, in this interval, we're assuming that I'm from -2 to 2, and x1, x2 are in that interval. Also, I have to assume that x1, x2 are in the interval -2, 2. Because it's saying, so you have at most 2 real roots in this interval. Also as part of the argument. So those 2 roots are inside the interval, but they're inside -2, 2. Do you see? So if I have those 2 roots, now the picture became, I have this scenario, and there's the c. The c is also between -2 and 2. So the real argument is we've just showed that this is true, and c is inside -2, 2, because it's inside, this interval is nested inside there, and that's what's really hard to see with these arguments. How do I contradict that? I take the derivative and argue that it can't be 0. In this case, it's going to be 0 somewhere, but it can't be 0 in this interval. And that's what we get, which is also their mean. It's really hard to see that that value is not in there. Let's do it first. Indeed, f prime of x is equal to 3x squared minus 15. And you're like, oh, well, normally they give me a plus, so I can just say larger than 0. It's never 0, and then we have a contradiction. This time it actually is 0. When is it 0? If and only if 3x squared equals 15. If and only if, oh, they're not too bad. This is 3 times 5 over 3, so the 3's cancel. And this is if and only if x squared equals 5, or x equals plus or minus the square root of 5, which is approximately equal to plus or minus 2.23. How are you going to get that? That's why I said it's mean. Can you gauge where that guy's between? I'll show you. So it says that, and you're like, well, I don't know about that business. Well, I'll show you a way to get out of that without having to know the decimal expansion of the square root of 5 is 2.236. ... He's important. He's part of the golden ratio. That's why I know. And I'm a nerd. We just found out that f prime of x is 0 if and only if x is equal to plus or minus root 5. Why is that a contradiction? I want to show that those are not in the interval -2, 2, and they're not. Root 5, so I look at 5. I actually cleverly want the perfect square on either side of these numbers. 4 is a perfect square, and 9 is a perfect square. Now I square root all 3 sides of this, which won't change it. That gives me 2 is less than root 5 is less than 3. So I know square root of 5 is 2 point something. Or it's strictly larger than 2. It being strictly larger than 2 tells me what? It's not in here. It's larger than 2. If you look at the axis, here's 2. Root 5 is 2 point something. It's larger than 2. It's not in that interval. So root 5 is not in -2, 2. And then for the other one, how would we do that? How do we do this? We know that the square root of 5 is less than 3 is less than 2. How am I going to get the negative guy? Oh, when we multiply by a negative number, it reverses the inequalities. So I'm going to multiply all of these by -1, and that's going to say -2 is less than root 5 is less than -3. Either way, what does that say? Root 5 is less than -2. I know those ones are hard to, you get negatives and everyone can't see it anymore. But he's also strictly less than -2, which says he's not inside this interval either. Nobody ever shows you that, so I thought I would show. What does that tell us? F prime of x equals 0 if and only if x equals plus or minus root 5, but those are not in -2, 2. And Rolle's implies we do have c inside -2, 2 with f prime of c equals 0, and this is the contradiction. May lightning strike you down. I can't have that my derivative is 0 somewhere in -2, 2, and then the only place my derivative is ever 0 is outside of that interval, -2, 2. This is a contradiction. Therefore, what had to be true? Use your words. F has at most one real root in the interval -2, 2. Number 5. For number 5, what we're going to do is use linear approximation to estimate e to the -0.015. Again, if you haven't seen this function, this is the exponential function, which is magic. What we have is this is e to the x. So e to the 0 is 1, we notice, and it turns out that e is the magic number that the derivative of e to the x is itself. So this is who this function is, the natural exponential function. E is approximately equal to 2.7182882814590455. So this is an irrational transcendental number, and these are the exponential functions. Their inverses are the logarithms. If you haven't seen this function, we'll do another in the other calculus review when we do linear approximation and or differentials. We'll use a different function. We'll use a sinusoidal function or a polynomial or something, or an algebraic function. So this is e. And coincidentally, because e is approximately equal to 2.72, roughly, approximately, what we're looking for is e to the -0.015, which is 1 over 2.72 approximately to the 0.015 is what we're going to calculate the approximate value of that thing. What do? We need the linear approximation. What we need is a nice function where we could compute with, and a nice value where I can compute in my function and the derivative. In this case, what we're going to pick is f of x equals e to the -x, and we're going to pick a nice value a to be 0. From that, what we're going to do is we're going to find the linear approximation of f of x at a. LA of x is equal to, the linear approximation of f at a is equal to the equation of the tangent line to the curve at a. So it's going to be a y equals mx plus b type equation. In this case, this is f prime of 0, x minus 0 plus f of 0, which is equal to what? Let's do the pieces first. First of all, I can do f of 0, which is going to be e to the -0, which is 1. And the derivative f prime of x is equal to -e to the -x, which is equal to, by the chain rule. And so f prime of 0 is equal to -e to the -0, which is -1. This gives us L0 of x is equal to f prime of 0, this should be a 0 too, a is 0. F prime of 0, which is -1 times x minus 0 plus 1, or the linear approximation of e to the -x at 0 is equal to 1 minus x. This is the linear approximation of e to the -x at 0. What we're looking at is e to the -x looks like this, and we're looking at the equation of the tangent line. This is the equation of the tangent line that we're looking for. This is the linear approximation. At 0, they're exactly equal to each other. Near 0, they're going to be approximately equal to each other, and then we're going to pick a value near 0, and then we can approximate this. So to approximate this value, what we have to do is see this value as the value of a function near a point for some function f. And then we're going to evaluate that way and use linear approximations. First of all, near a equals 0, they say, f of x is approximately equal to L0 of x, which is 1 minus x in this case. Therefore, what are we going to pick? We're going to pick now an x value, which is 0.015, and then that means that's near a equals 0. And that means e to the negative 0.015, which is equal to f of 0.015. F of 0.015 is now approximately equal to L0 of 0.015. And that is equal to this, a linear function. So that's just equal to 1 minus 0.015. That's the linear approximation. Let's compute that specifically. This tells us that we get equals 1 minus 15 over 1,000. And this is equal to 1 minus 3 times 5 over 200 times 5. So this is 200 over 200 minus 3 over 200. I multiplied 1 by 200 over 200, my favorite dirty trick. And so this is 200 minus 3, which is 197 over 200. That is the approximate value of e to the negative 0.015. If you don't like the fractional avatar, let's do that also. Give me a second. If I want the decimal expansion of 197 over 200, what I have to do is long divide 200 into 197 and write point zeros and find the decimal expansion. The way to do long division efficiently is the game we do in every step is how many times does 200 go into 197? 0, we say, and then we're going to keep the point there. And then technically what we're doing is 0 times 200 is 0. And so we write that out 0, and then we subtract, and we get 197, and then we bring a 0 down. Now in the first real step, now what we're going to do is we're going to play this game. And if you don't have this, and you haven't written out the multiples of 200 already, this game sucks. So without that, if I stand in front of it and you can't see it, what the game you're trying to play is, and they never pointed out, you should have wrote this down first. How many times does 200 go into 1970 without going over? That's the nearest multiple I need so I can subtract. If I look on the list, 2,000 times 10 is too much, times 9 is just right. It's 1,800, which is less than that. So it's going to be a 9. And I'm going to get 1,800. Then we subtract 0, 7, 1. I bring another 0 down. Now I do the same thing. How many times does 200 go into 1,700? I look and I see, it's 8. And so I get 1,600. I subtract. I'm going to get 0, 0, 1. I get 100, and then I get 1,000. And then, there it is. It goes into there exactly 5 times. And I get 5, and I get 1,000, and my remainder is 0. What does that tell me? 197 over 200 is equal to 0.985. The 0 is repeating, technically. Let's clean that all up. And after I use long division, there's your crash course in long division to get the decimal expansion of fractions. Fractional avatar of a rational number. Decimal expansion avatar of a number. What did that tell us? That told us that e to the negative 0.015 is equal to f of 0.015, which was approximately equal to the linear approximation L0 of 0.015, which was 1 minus 0.015, which turns out to be the fraction 197 over 200, which is equal to, in decimal expansion, 0.985, or e to the negative 0.015 is approximately equal to 0.985. Now I really need to check. Get your device out. 0666. Boom, 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 boom. No, not that number. What do I want? Get your electronic device out. And what can we do? I gotta be fancy with it. I don't know how to use the calculator. 0.15 minus E. It tells me in my magic calculator that e to the negative 0.015 is approximately equal to 0.985111931 9603063 . So we got it to 3 decimal places. This is how you approximate values without a calculator. Next question. Number 6 wants me to compute this limit or state why it doesn't exist. And I'm going to 0, and I've got a tan, which is a trigonometric function in there, so I'm kind of scared what's going to go on. What we need to do first is, the first mantra is, if I have a limit and it has a trigonometric function in there, I think maybe I want to use squeeze theorem. But in this case, I see that I shouldn't be using squeeze theorem, probably because tan is unbounded, where sine and cosine are bounded. So instead, what we're going to try and see is, if we can see, what we want to see is these types of limits. The limit as theta approaches 0 of sine theta over theta equals 1, and or the limit as theta approaches 0 of cos theta minus 1 over theta equals 0. We're looking for these two limits a lot of the time, and what they're actually saying is, we'll just do it for one. In there, what they mean is, as x approaches 0, say, of any ax over ax, whatever's inside the argument of sine has to be over that same value. That will always equal 1. And so I see an a is 2 here. And then we're going to turn tan into sine over cosine and try to see these types of things inside there. Let's do that. Indeed, the limit as x approaches 0 of x cubed over tan cubed 2x is equal to the limit as x approaches 0 of x cubed over sine cubed 2x over cos cubed 2x. If you want, multiply the top and the bottom by cos cubed 2x. And then what do we get? Here we're going to get cancel, cancel, and we get equals the limit as x approaches 0 of x cubed over sine cubed 2x times cos cubed 2x. 1 over tan is cotan. So now that cotan is cos cubed over sine cubed. Now that I've cleverly written it like that and I have sines and cosines, I'm trying to see sine cubed over x cubed, and what's going to happen there. I need a 2x. How are we going to do that? First of all, I need it to go into the x cubed, so I need to put 2 cubed over 2 cubed, or 8 over 8 is what they're going to do. This is the limit as x approaches 0 of, I need it to be of 2x cubed. Sine cubed actually means this, lazily, cubed. And so I need 2x cubed. I need a 2 inside there is what I see. So my move is going to be 2 cubed over 2 cubed is what I'm going to multiply it by, times x cubed over sine cubed 2x times cos cubed 2x. I'm no longer worried about cos also, because cos of 0 is 1, so it won't be a problem whether it's on the top or the bottom. So that's just going to be 1. I'm worried about the sines. Now I can combine those guys. This is equal to the limit as x approaches 0 of 2x cubed over sine cubed 2x times 1 over 8, the 1 over 2 cubed, times cos cubed of 2x. Finally, this is 1 over 8, the limit as x approaches 0 of 2x over sine 2x cubed times cos cubed 2x. We'll bring that up and around. That's equal to 1/8, the limit as x approaches 0 of 2x over sine 2x cubed times, first I'm putting the limit onto both of these functions, times the limit as x approaches 0 of cos cubed 2x. Now what I'm technically doing is switching the continuity of these limits, which is going to be 1 over 8. Now I can do cubed times this limit is also just 1 cubed. I'm going to do that. This limit is 1 cubed. And so this limit is, I can switch the limit in a continuous function, they tell us. So x cubed, or the cubed function, is continuous, so I'm going to switch those. This is the limit as x approaches 0 of 2x over sine 2x, and then that's 1 over 1, that limit. So this gives us 1 over 8 times 1 over 1 cubed times 1 cubed, which is 1 over 8. This limit exists and is equal to 1/8. One more. Okay, for number 7 and the last one in this first part of calculus review problems, what we're going to do is we're going to do an optimization problem. We're going to find, we're going to model an area with respect to some function and some dimensions, and then we're going to take the derivative, and then we're going to optimize this and say that this is the largest area that we can have, but this is the question that we're given, and if you don't like these, the first thing we have to do is translate this and try to get up some equations and some variables and set up everything in a picture possibly to try to draw what's going on with this. What we're going to do is, it says I have a rectangular plot, has a river on one side, so we don't need a fence for that part, and we have 3 sides to be fenced in. If we have 800 meters of fence to use, what is the largest area, and therefore possibly what are the dimensions of that area or the rectangle that we're going to make, having the 3 sides to enclose? And we want to know what's the maximum area we can create if we have 800 meters of fence, which is going to be the perimeter. So again, we're always going to have 2 things essentially. What we are going to have is, in this problem, they're talking about 2 dimensions. They're going to talk about the vertical dimension of this box and the horizontal dimension. Let's call those respectively x and y. If I do that, now that I've set what those quantities are called, those are my 2 variables. Once I have 2 variables, I'm going to need 2 equations to set up those variables so I can eliminate one of the variables in terms of the other variable, and then we can differentiate a function of a single variable and see what the minimum or maximum is depending on what the question is. What does that mean? We have an area which can have a formula, which we can have, and then a perimeter which will have a formula, and then we have 2 equations we can set up from those area and perimeter formulas dependent on x and y. Let's do that. It says the perimeter, which they gave us, is 800, is equal to x plus 2y. This means that the easiest one to solve for is x, so I'm going to be lazy. This tells me that x is equal to 800 minus 2y. So I use the equation they gave me and the value they gave me, 800 for the perimeter, to solve for one of the variables in terms of the other variable. In this case, I chose to solve for x in terms of y because it was easier. I didn't have to divide by anything and get any fractions. You could solve for y in terms of x if you want, is what I'm saying. Once I've done that, then I use the other equation to, and why do I know I use the perimeter first also? It asks me to talk about and find the largest area. So because I want the largest area, what I'm going to have to do is write this as an area of a single function. In this case, I'm going to use area of y. And then we're going to differentiate that with respect to y, and then we're going to find a maximum or a minimum. We want to know what the largest, so we're going to try and find and argue for a maximum value in our function. So let's do that. The area is x times y, and that will tell me that the area is, what was x? X was 800 minus 2y times y. This now gives me an area of a function of 1 variable. Let's write that down. The area of y is equal to 800y minus 2y squared. What do I do with that? Now I have a function which is on an interval, and where's y? Y is in the interval 0, infinity. And it's an open interval, so we can't use the closed interval test to say that we have a maximum and a minimum for any continuous function on a closed interval, because we have an open interval. So what we're going to do is something slightly different. We'll see in a second. But that says, because our length has to be, it can't be 0, otherwise we have no fence length, and it can't be really infinity, because then that means we have some infinite strip or something like that. So it's going to be somewhere in there. Actually, it's going to be somewhere much bounded by the perimeter, I'm going to guess, but we'll see. What do we now have? Once I have that and I have the domain of my function, I'm going to try and argue that in this domain, 0 to infinity, for this function, a has an absolute maximum, and therefore the largest area that we could find with respect to the y coordinate, and then finding the y, and therefore the x will give me the dimensions when that happens. Let's take the derivative and then see what we can see. A prime of x is equal to the derivative of this. Because it's a polynomial, I'm just going to get 800 minus the derivative would bring down 2, so 2 times 2 is 4, and then y. Now this is linear equation, one equation and one unknown. I just solve for y. This tells me that y, 4y is equal to 800, or y is equal to 800 over 4, which is 200. So we know now that y is 200, and what are we going to get? That's going to give me, what does that give me for my other dimension? First of all, is this a maximum or a minimum, can we argue? Let's do that first. We found that our function of one variable, y, which was the dimension of the, and then we have the river over here, so this is y and this is x. We use the perimeter equation to find what x was in terms of y. We isolated, we got a single function. We take the derivative. We know that the derivative is 0 at y equals 200. So this function only has one critical value, 200. Then we're going to try and argue that that's a maximum, and the largest value in the interval. What's the interval? 0, infinity is the domain of y. Y is in here. So we want to show at y equals 200, we get the absolute maximum. This is saying we have 0, we have 200, and then dot, dot, dot. It's saying that we're going to have the maximum at 200, and then we have to argue at here and at infinity what's going to happen to this graph. This guy. This is the dimensions of the box, y, and x. We have one critical value for y. What does that tell us? Again, we want to look at when is this 0. Actually, we can actually factor 4 out of that. So we get 4 times 200 minus y equals 0 is the linear factor. So what are we going to get? 0 to 200 is what I want to look at. 200 to infinity, because that's our domain. What do I want to look at? 200 minus y, which is a prime of y. Well, 4 times that, but the 4 won't make a factor. And then I want to know what happens to a of y. First derivative test, increase, decrease, local max and mins. Now what I'm arguing in here, in 0 to 200, I see that this value would be positive. Pick any value in there. 100, 200 minus 100 is a positive value, so I'm going to get positive. That means my first derivative is positive. That means I was increasing into 0 into 200. So my function is increasing into 200. And then in here, if I'm larger than 200, pick 300. 200 minus 300, negative. So my first derivative is negative. And that means my function is decreasing out of 200. And then so we're going to be a parabola that's looking like that. And then now what I have to do is argue that this limit at this boundary doesn't blow up and it's just going to be 0, and this will become arbitrarily large negative. So my largest value, actually my maximum, is exactly occurring at 200. What does that give us? Up, up, up. That gives me from this table, this says we have a local max at y equals 200 in the interval 0 to infinity. We want it to be an absolute max. is what we want. How do I change it from a local max to an absolute max? In a closed interval, you just check the boundary points and all critical numbers and we're done. But at these boundary points, we have 0 and then we have negative infinity are our boundaries, and it's open, so I can't use the closed interval method for this. Instead, what I show you is the limit as y approaches 0 from above is going to be the limit as y of 800 y minus 2y squared, which is 0. 800 minus times 0 minus 2 times 0 squared is 0. So that says that this limit is 0, which is definitely less than my maximum at y, which we're going to compute in a second. And then it says at my other boundary point of this interval, infinity, the limit as y approaches positive infinity of 800 y minus 2y squared is negative infinity. So it just gets smaller and smaller, not bigger and bigger. And so that tells us that because of these arguments and the fact that now at 200, a of 200 is equal to 800 minus, or times y minus 2 times 200 squared, or the area was x times y. What is x? X was, from our original equation, remember x was 800 minus 2 times y, which is 800 minus 2 times 200, which is 800 minus 400, which is 400. So this area cheating is 400 times 200, which is 80,000. And what were the units? Meters squared. But what that's saying is a of 200 is 80,000. A of 0, this open interval point, is 0. And then at the other open end point, we have negative infinity. It's close to negative infinity, so it's getting more and more negative. So this is an absolute maximum. So the largest area we can have for the rectangular fence is 80,000 meters squared is the largest area you could have, having an 800 meters for the perimeter. Please subscribe below and hit the notification bell, and then you will get notifications for other videos in this series and other series. I'll see you next time.